Okay, so what we're going to do is we're going to continue on our conversation from last time. What did we talk about last time? Bias. What's bias, Dennis?
Kind of like you do something based on.
Well, so you're thinking of bias in kind of the normal sort of everyday language. I'm talking more about the statistics bias. I'm talking about sampling bias. That's what we talked about last time. Sampling bias. Remember we talked about 3 different sources of sampling bias? What are those 3 sources? Name one. Anyone? Undercoverage. Survivorship. And Audrey, you had your hand up. You actually raised your hand.
Say undercover.
Okay. Well, can you tell me what undercoverage is?
So that's where, isn't that where you're including like a population and like you're excluding some people, like
like the way that you built your sample.
Yeah.
You can't include certain elements of the population, right? They're just like by the design of the sample. What'd you say, Amanda?
Self-selection. What was self-selection?
Like when there's like a certain people that can participate. There's people that don't. Like
because people can choose to participate or not, right? Exactly. So it's a self-selection. And what's the last one? I heard it. Survivorship. And what's survivorship?
The idea that since you're in some kind of process, therefore that kind of bias, like if you take the therapist example, if you stayed 6 months with the therapist and you're looking at whether that therapist was good, the bias is that if the person stayed with the therapist, they're probably going to like the therapist.
So truly bad therapists don't have any samples, right? They have no one that survived getting through them, so we don't know. We don't even know they exist. Right? But we have to be really careful. So all these are sources of bias, but just because you may be not including a certain part of the population, or just because it's some sort of test that people have to survive, or just because the people are choosing to be included or not, does not mean there is a bias. We talked about this in great detail. If the people who are excluded or opt out or don't survive are systematically different than the people who are included, who are opted in, who did survive, that creates the bias. But if there's essentially no difference between the survivors and the non-survivors, between the people who are included and people who can't be included, then it's perfectly fine. Right? The whole point is this way of gathering could create a bias. So, and like we talked about, it does matter what you gather. It doesn't matter in the relationship. If we're asking like what you plan to do for a living after school, and I only ask people in this room, that's obviously an undercoverage bias. I can't include non-business criminal justice majors, right? I'm certainly don't have a representative sample of all majors. Naturally, the major you have is going to impact what you're going to do. If, however, I asked you what your favorite color is, then there's really no relationship between major and favorite color. So that's probably not biased. I mean, maybe it's biased in some other way, like I'm only including young people. Maybe young people, maybe not represent the population because maybe there's some generational differences in color preferences or something like that. But generally, you have to come up with a link between the bias and what you're actually looking at.
That could an important selling point.
We also talked briefly too about the difference between survivorship bias and undercoverage. What's the difference between the two? Do you remember? Because they seem really similar. Yeah.
Survivorship, you don't know who you exclude until after, or undercoverage, you know who you excluded.
Exactly. We can identify people that we can't include, but we can't identify survivors beforehand because we haven't created the little test yet. Right, that subtle little test we created. Okay. Good. Any questions about that? No? Fantastic. So now let's move on to what we're discussing today of data and displays. I sometimes I didn't do this at first, but I discovered this is an important thing that I need to do because many of you have maybe encountered this idea before, but haven't really internalized it yet. Maybe you've never been explicitly taught it. So I think it's important that we cover this one little area. Before we get started, because this comes up a lot in data and displays. If this value is expressed in terms of in millions, how much is it? So this is 3,000, but it's in millions. How much is it? Yeah. It's 3 billion. How did you know?
Because there are obviously
Exactly. Come over is going. Did everyone, by the way, know that if I take 3,000, it's expressed in millions, that's really just 3 billion? Right? How many of you have ever taught that? Right? Oh, some of you have, some of you haven't. Right? And it's fine if you haven't, because I assumed that they taught this, but I mean, schools are very different. Some things don't always stick. So I'm happy to go over it. This comes up a lot when we talk about data and displays, because in data and displays, it's all about trying to convey information in a small physical amount of space. And so writing takes up a lot of space. So you will often see data or just charts summarized in terms of in millions or in thousands or in billions or something like that. And so we should be comfortable converting. And not just converting from, say, this is 3 billion, but be able to say if it's billions, it's 3. If it's in millions, it's, if this was in thousands, for example, what would this be? What number would be here if we converted this from in millions to in thousands?
3 million.
3 million, right? We would go in from millions to thousands is one step. And so we would move that decimal place 3 spaces over, and we would have 3 million in thousands. So this is the job openings and labor turnover survey. This happens every month. The good folks at the Bureau of Labor Statistics ask a bunch of questions and figures out a bunch of data about how many people were hired, how many job openings there were, how many people quit, how many people were fired. And it does this every single month going back to, I think, 2007, I want to say. And so you can go, if you just do a Google search and you do JOLTS and you pull up BLS, you can find it. Let's do the one screen search. I'm curious what information you are curious about. Like we can do total non-farm, we can do total US, do the level. What are you interested in about? Do you want to do job hires? Do you want to do total job openings, hires, separations, or a subset of that separations, layoffs, quits? Which is anyone in layoffs? Oh, you sort of smiled too when you said that, which is, all right, let's do layoffs. And oops. Oh, okay, no, we got it. Sometimes you have to hit the actual get data and then hit the button, but I guess it works. So here we have, oops. Okay, anyone want to tell me how many people were laid off in it only goes back to 2009, that's fine. How many people were laid off in November of 2019? And that P, of course, means it's preliminary. So that data, that information might change as they finalize and they get additional sources. How many individual people were laid off, roughly, in November of 2019? Exactly. Because it is, as you know, in thousands. Right, it's in thousands. So you have to look for that. You have to make sure, if you looked at this and you didn't realize, you'd be like, oh, it's only 1,749 people were laid off in the entire United States. That's weird, right? It's in thousands, so always check for that. Generally, here's the pattern to follow. So we have trillions, which I think is usually abbreviated with a T. Billions with a B. millions with an M, thousands with a what? K? Does anyone know why it's a K?
Because it's a lot.
Kilo. Yeah, or kilo, maybe it's kilo, but I think it's kilo. It's kilo because of kilogram. What is a kilogram? 1,000 grams. Right. So a kilo is literally 1,000. So that's the Latin for us. And then I guess we just have it in ones, which it doesn't really have an abbreviation, it's just ones. When you go from here to here, when you go down, every step that you go down, you move that decimal 3 places. So 3 trillion becomes 3,000 billion, or 3 million million. In other words, move decimal points 3 places to the right. As your descriptor gets smaller and smaller, the actual number you're describing should get larger and larger. So every one of these steps is 3 places to the right. The other way, it's exactly what you might expect. Move the decimal point 3 places to the left. As your descriptor gets larger and larger, the actual number that you have should get smaller and smaller to compensate. Any questions? Yeah, I get 340,000 either. Right. You also get that. Yep. No, you always had to. I know it's tricky, right? Going from the really large number to rounded is more intuitive because we're saying the commas, right? When we're saying, but of course, in practice, we might want to go the other way too. So, all right, we move 1, 2, 3. That becomes 0.34 million. 1, 2, and then there's a 0 there. 340, 340,000.
So if we moved it 3 to the right, we would just be 33.4 billion instead of 3.
Well, if we move it 3 to the right, that means the decimal point is here. So the millions, the billions become millions. So 0.34 million. And it makes sense, right? Because, this is less than 1, so it should be less than a million, and indeed it is. Let's imagine we have data like this, for example. And we're trying to figure out how common are these layoffs? Like here we see obviously a lot of layoffs at the top here. Where am I? There it is. There's my mouse. Right here, right? We see a lot of layoffs. Naturally, this is the recession, and then it goes away. Looks like it's still pretty low, but sometimes it pops up a bit. What if we're curious how common different kinds of layoffs are, how levels of layoffs, right? Like if we were to get a dispersion, some sort of indication, right? Because this by itself isn't very helpful. Like, I guess you can say there aren't many layoffs historically. Maybe it's a little bit hard. You don't really get a sense of the larger picture. How would we do that? How would we visually describe this data? Yes?
We can maybe put it into a graph.
What do you mean? Oh, like over time? Sure, absolutely. So we could, so what's nice is that this is a time series. So we could do that. We could see, that's a really great way to do it. And we'll talk more about that, I think, toward the end when we talk about data truncation. But let's imagine we were just more interested in like, when we get new numbers, we want to get a sense of if they're high or low. Maybe we want to get a sense of how common that kind of result is. Like, let's imagine that 1749 is final. It's, of course, preliminary. Like, well, is that a common result, 1749 historically? Do you get a sense that there's a lot? Is there any other one that's 1749? Do you see any other 1749s? No, right? So does that mean it's not a common result? You guys are really quiet. How would you figure out? Yeah.
So I guess it depends on what you mean by BSAD.
Okay.
If you don't see any other BSAD 17 lines, or like formula numbers with all the
Mm-hmm.
kind of like a number.
Yeah. And you know, like, sure, there are no 1749. There is a 1755. Is that really that different? There's a 1711. Hell, just last, you know, that's less than a 50 difference. The 1795. Oh, there's another 1795. I don't think they win the match. So, you know, there's 1748, right? Are we going to say that 1749 is so different than 1748? So, in other words, one thing we could do is we could define ranges. We could say anything between 17 and 1750, and anything between 1751 and 1800, something like that. And then we get a frequency within each of these ranges. And we call that a histogram. So this is option 1, explain data, histogram. In other words, what histograms do is they take quantitative data and they turn it into categorical data. Now, we talked about how you should not do the other thing. You should not take categorical data and turn it into quantitative data. Why not? Remember why not? Why shouldn't we, like, you know, trying to figure out what the average major is? We'll assign 1 to accounting, we'll assign 2 to Asian studies, we'll assign 3 to another thing, 1 to architecture. What's wrong with that? Yeah, you can't put a number in a category, right? Later, we'll talk about how you can sort of do that with a dummy variable, but then you're just really you're just creating a lot of variables. But generally speaking, you can't turn a number in a category because the number you will put on that category is going to be, by definition, arbitrary. But you can turn categories, you can't turn numbers into categories, even if you can't turn categories into numbers. You do that by creating bins or ranges, creating ranges or bins. You count how many observations are in each bin. Sometimes it's a frequency count, sometimes it's a percent count, but it all amounts to the same basic entity. Now, there's a little bit of arbitrariness in the size of the bin and the cutoffs of the bin. Cutoff. Like for this data, for example, I could say, oh, you know, maybe it starts at like 1700, or maybe it looks like I have a 1600 and 1500. So maybe it starts at 1500 and goes to 1600, and 1600 and goes to 1700, and 17 to 18, 18 to 19, 19 to 20. I could do that, and that would not be incorrect. I could also, though, do 15 to 1550 and 1550 to 1650 and so forth. I can make each segment of 50. I could do, I could technically do 1593 to 1603, or I can make each distance a 7, so I can do 1593 to 1600, 1600 to 167, so It's totally arbitrary. Granted, there are some ones that make sense, some ones that don't. You don't want to have so many bins because each bin will be represented by a bar graph. You want so many bins you can't really tell what's going on. But the advantage is the more bins you have, the more you can see what's going on within the bin. So there's a little bit of give there. We also, therefore, don't know what's going on within a bin. We don't know what's going on within. You can have this range, and you can say there's 8 or 10 observations within this range, but you don't know, are those 8 or 10 observations mostly concentrated at the beginning of the range, or toward the end of the range, or maybe they're in the middle, or maybe they're evenly dispersed. You don't know what's going on within each bin. That's going to be a constant problem whenever you turn these numerical data that can be anywhere to these ranges, because you don't know what's going to go on in the range. Any questions? Okay. Let me show you how to do it in Excel, because Excel makes it very easy. We're going to pop over to, let's just pop over here. And if you go to my website, please, hold on, don't save it. If you go to my website and you go to dataset 0, let's go to our friend dataset 0. Dataset 0, as you recall, has data on individual majors and median wages, median salaries for those majors. And then we wait patiently while Excel loads. There we go. Enable the editing. And maybe we're curious what that dispersion is. So what we can do is you can just highlight the data that you care about. So I am not highlighting that 50% there. I'm just highlighting the data. Does everyone have this, by the way? Most of you looks like you do. Under Insert, you will see that there is this chart section here. This chart section is really fun. You can create any number of charts or data displays simply by highlighting the right data and then going to the chart and hitting a button. And that's what I'm going to do here. I'm going to go to this, I'm going to hit a button. And in the middle, you see there's a histogram button. And you can, of course, figure this out just by mousing over anything. Right there, this insert combo chart. We're not going to deal with that. Here we go. Insert statistics chart. Kind of looks like a histogram. You hit that button, you see a histogram. And then immediately it generates it. It will automatically create your ranges. It will automatically put the data. It will automatically create the frequency. So we see there are a lot of observations that are toward the bottom. And what is the size of these ranges? Looks like it's always 13,000. Now, you'll note too, if you look way at the bottom, that there's like a bracket and there's open parentheses. You'll see these, or you'll see these. You see that at the bottom with those numbers? What do those mean? Yeah?
The range of the top one is included, and then the parentheses it's not included.
Exactly. So way at the bottom, you'll see this goes like, let's take the second one, 55,000 to 68,000. It's 55,000 not included in 55,000 itself, just more than 55,000, or up to and including 68. That's what that closed bracket means. Because you have to, well-made charts make this really clear. If you make 55,000, which one of these two things do you go into? So if you make 55,000, you clearly go into this one because it has a bracket right here. Now, there's a bunch of things you can do to this chart. If you want to make it pretty, if you use the plus button, you'll see you can add axes titles. You can throw in some data labels if you want. You can do a bunch of stuff. We're not going to get too much into that. You can change the title if you want. And you can do all kinds of things that make it prettier. But that's more or less how you can make this chart. One thing you have to keep in mind, though, a major weakness of this histogram button is that this range of 13,000 you are stuck with. It was generated by an algorithm based on the data it had available. You can't change it. It's one of the things that drives me crazy. Like, the histogram is super great because it's fast. It literally takes, it basically takes no effort at all. But it's like, why is it 13,000? That's kind of weird. Why isn't it 10? Right? Why isn't it like 15? If I wanted to have more than 5 bins, how do I do that? So I mentioned in the notes how you can figure that out. I used to teach it. It's a rather time-consuming thing to teach, so I've stopped teaching it. If you really want to know, I linked a video that shows you how to do that in the notes. I will mention, though, the first step to doing that, because this is going to come up later in Unit 3, so I want you to have lots of practice doing it, because I want this to be smooth. If you go to the Data tab, you should see Data Analysis, or you might see Data Analysis. How many of you see Data Analysis on the far right? Right. Some of you do, some of you don't. Here's how you make it show if you don't have it. Go to the File section, and everyone should do this even if you do have it, because you want to make sure you can access it. If you go to the File section, way at the bottom, you'll see Options. Under the Excel options, you will see the add-ins on the left near the bottom. Click add-ins. At the bottom of this, you will then hit Excel add-ins. You'll see the Excel add-ins. You'll hit the Go button at the bottom. If the analysis tool pack is checked, then you'll see a data analysis. If it's checked and you don't see it, then you want to turn it off and then turn it on again. That's how you fix anything. Note that if I turn this off, data analysis goes away. Options, add-ins, Excel add-ins, analysis tool pack. Okay. You can also hit the VBA if you want. It doesn't matter which one. I tell you about data analysis because when you click on data analysis, it has more advanced functions in it, one of which we'll be making heavy use of, called regressions. Don't worry about regressions yet. We'll talk about that in Unit 3. But you will see that one of the options is histogram. And to make this option, you then tell Excel what your bins are, and then you use the histogram function to, it will essentially count everything for you. And then it'll create a little chart that you can then make a histogram out of, based on these bins, how the frequency for each one. But we're not going to get into it. It's rather time consuming to explain. And I won't test you over it either, but that link that I linked to in the lecture notes is there in case you're curious. So we have done one strategy where we define bins, and note these bins are the same size. They don't have to be the same size. For example, here's data. Let's see if I can pull it up. Here's data from the Iowa caucuses. Note that what they did, it's still coming in, but what they did is they have bins for ages, and they say 17 to 29, 30 to 44, 46 to 64, 65 plus. Are these bins the same size? Are these the same ranges? Right? You're shaking your head? Why are you shaking your head? I agree with you, you should, but why? How do I know what the sizes are? Because I'm looking at the ranges. I'm looking to see how they define each one of these bins. So this is bin 1. This is 17 and 29-year-olds. The very first one is 17 and 29-year-olds. Right here. That is how many different ages? 13, because you have to include 17. I know, I always do that too. Right, 13 different ages. How many ages is this, the 30 to 44? 15, again, you have to do the thing. 15, right, 15 different ages. Right, so immediately not the same. This one is like 20 ages, the next one is 20 ages, 45 to 64. And the last one is technically infinite ages. Right, but in practical sense, it's still it could be like 30 in all practical sense. There's a lot of old people in Iowa. I'm from there, I know. I grew up there. Once. In 2000. No. Because there were only 2 candidates. It was Al Gore and Bill Bradley. So the cool caucuses are when there's like lots of candidates, and then some people don't become viable, and so people are yelling at them to come over to their side. And, there's all this like negotiate. That's the circus of it. I didn't experience that. It was like Al Gore and Bill Bradley. And there's not really anything going on. I don't even think Bill Bradley was a viable candidate. Those were the days. No, I went to college in Wisconsin. So I did leave, when I graduated high school. But I still go there to visit the parents with the kids, and the family, I should say. My wife goes to. Okay. Any questions on this? So generally, though, they're about the same size. The fact that these are not about the same size is more an artifact of, like, we recognize people in their 30s are different than people in their 20s. This is like prime working age right here. These are people who are generally retired. That's why they broke it up that way. But generally, we try to keep them the same size. But what happens if we mix it up some? Let's go back to our data. What happens if instead of making them all bins all the same size, we make the data all the same size? In other words, or I should say we make the bins not have the same range, but have the same number of observations. Have the same-ish range is a histogram. The bins have the same number of observations is what we call a box plot. Sometimes call them a box and whiskers plot. And it's that way because it divides the data into 4 bins looking like this, where there's a box and then there's these little lines coming out like whiskers. Has anyone ever seen a box and whiskers plot before? All right, a lot of you have. So can you tell me then, Diane, what is it made out of? Like how is it formed? Like how is it defined?
So on that end, it's the lowest number of whatever.
Yep. So our min value, our minimum value.
Right. And then on that one, the max is the highest value.
Exactly. So there's our max.
And in the box, on the left, it's we call it 1.
You can call it the first quartile.
Yeah, first quartile. In the middle is
Also known as the, anyone? Second quartile. Second quartile is the median. And what's this one? Third quartile. Now, if you are not familiar with the idea of quartiles, keep in mind that you are. Because this data, let me shrink this. I'm just gonna show this over here. Has exactly the same thing. Here's the first quartile, second quartile, third quartile. In other words, 25% of accounting majors get paid $47,000 or less than 47,000, right? That's the cutoff point. Half get paid more than 69, half get paid less. 25% get paid more than 103,000, and 75% get paid less. So this is exactly the same idea. Each one of these segments represents 25% of the observations. That's why we call them quartiles. Like quart, like 1/4. That's why also we say the median is another way of saying the second quartile, because half the observations are on one side and half the observations are on the other. Note that because of the way this is set up, these ranges can be very, very different. This is a huge range. Right? This is a very small range. This is a relatively small range. Right? It can go all over the map because we fixed on how many are in each bin. I don't care what you make the bins look like, just make sure 25% of the observations are in each bin. And that means that the bins can't be fixed in size. They have to be able to vary. Just like before, we also don't know what's going on inside each bin. We don't know what's going on inside each quartile. All the observations should be counted right here with maybe like one right here, and this is 25% when most of them are right here. Or maybe most of them are right here. Or maybe it's evenly, we don't know. Don't know what's going on inside. But we can create a box and whiskers plot or box plot, just like we do with a histogram. Any questions, by the way, on this and on what they basically look like? Okay, so highlight it again. Make sure to select off the chart, because otherwise it'll replace the chart. Select off and re-highlight. Insert. You will see when you select the histogram button again, there is a box and whiskers option. And for some reason, it decides it's going to make them vertical and not horizontal. I don't know why. I've looked into trying to see if there's an option where you can just flip them. For some reason, this doesn't exist. Just rotate it. It doesn't exist. I think there might be something you can get where it'll automatically do that. But generally speaking, it's just going to be vertical. This is not too easy to read, though. There is that median. That's really hard. I don't know why it defaults to this. Let's do that. There we go. And now what's nice is we can put these side by side. Note the symmetry between these two, the low salary areas in the histogram. And note, that's what we see here. Because there are so many salaries that are located in the low end, then we very quickly get to 25% of observations right over here. And therefore, there is not a very big range. And we get to 25% of observations again right here, very quickly, so not a big range. But it takes a lot of observations to get to another 25% on the high end, so there's a much larger range up here. How many observations do we have? Let's see, we have 20, so that becomes 35 total, 43, 48, I think this is 50 total? Well, 49. 49. So you do the math, and each one is about 12 observations. So this is the 12 observations, this one, plus some of these. All right. Well, here, almost 2 quartiles, not quite 2, but almost 2 quartiles located in just one of these bars, or one of these ranges. So that's why it's so close together. And you can see both are useful. Both kind of tell you slightly different things based on slightly different criteria. But there's a lot of overlap between these approaches. Questions? Okay. Let's talk categorical data. So generally speaking, categorical data is got categorical data is often done in terms of maybe a bar chart or a pie chart. It's similar to a histogram in the sense that each one of the values you have along the x-axis is a kind of range, or in this case, a category. Because you can think of a range as a category. Sometimes, too, pie charts include categories as part of their wedges. You know what a pie chart looks like in all likelihood. This is the one area where people generally don't have trouble with. What's a pie chart? It's pie, right? Circle. That. Sometimes there are means made out of it, right? You know what a pie chart is. 100% of values, et cetera, right? And each wedge represents a certain percent. And then each wedge represents one of the categories. One of the problems with pie charts is they're a little weird. Let me show you what I mean. Where'd it go? There it is. This is from the notes. Let's take a look at B. In B, which value is larger? Blue or red? Blue, you say blue? How many of you think blue? About blue, the same. How many of you think red? You're not going to make a statement? Why not? Without, what do you mean? This is the evidence. You have the data right there. Okay, well, so, all right, if you can't see, that's going to be hard. Okay, so if you're colorblind, that's going to be an issue. But for those of you who can see both colors, that's, by the way, another problem with some of these that can come up. But that's another issue. You can recolor it. How many of you are confident they know which one is larger? All right, no one seems to be confident at all. Yeah? Which one is larger? Blue, you think blue. How many of you suspect, at least suspect it's blue? All right, a few of you. How many of you suspect it's red? A few of you. How many of you suspect they're the same size? A fair number of you. All right, most of you suspect they're the same size. And indeed, you are correct. They are the same size. Here's the same thing, right, but bar chart form. But note that, oh, David, what did that add then? Because they are the same size. Most people thought they're the same size. But now, are you confident they're the same size? Yeah. Right. Does anyone now think that blue is bigger? Right. Does anyone now think that red is bigger? Right. No one. We are all now on the same page, right? Before it was tricky, right? Yes, most people correctly identified them as being the same, but a few people were going in one way, a few people were going another way. There was some ambiguity, which is not good for conveying information. But now we are all in agreement. One of the problems with pie charts, while they are very common and you should be familiar and comfortable with them, is that they are judging size based on a two-dimensional area. Right? And not even just a two-dimensional area. Not even an area, but an area that's kind of awkwardly shaped. It's like a triangle, but it's got a curved part, right? While a bar chart is measuring size based on one dimension, who's tallest. Sometimes, and it drives me crazy when I see this, sometimes you see like bar charts where they don't have like a line, they just have like a cute little like graphic or something of like, I don't know, what's, who makes the most like potatoes, and they'll have like a really big potato and then like a smaller potato and a small potato. I'm like, am I measuring the height of the potato or am I measuring the size of the potato? I don't know what I'm doing, right? That's weird. I like it when they make the potatoes, make it really skinny, right? Keep it the same height. That's much better.
Or just making a fry.
Or just making a fry, even better, right? So, I mean, bar charts are a bit more intuitive. Pie charts are more common, but you should be aware that pie charts are sometimes a bit deceptive. I think pie charts probably are maybe a bit more densely packed. It's possible, you know, they're a bit more aesthetically pleasing too, right? Because you don't necessarily have to have this axis right here. It tells you what's going on. So you could argue that there are some aesthetic benefits of pie charts, but sometimes they're just kind of weird. Good pie charts, though, would just give you the numbers, assuming you can fit them in. Look at this one. This one looks like maybe they're all about the same size. Nope, they're totally different. God, pie charts are stupid. But, you know, I don't want to say they're always stupid because there's some benefits. All right, questions? Great. Okay, let's now go to scatter plots. So far, we've been only working with one variable. Now let's work with two variables. And to include two variables, we are going to make a simple XY plot. You've probably seen this before. How many of you see a scatter plot before? All right. So we have a variable right here. Another variable 1, another variable right here, variable 2, and then each dot represents what? Each dot represents what? Come on, each dot represents an observation. Did you say that? I just didn't hear it? Yeah. Each dot represents an observation. And for every observation, there are 2 bits of data, one for one variable, one for the other. And this is very helpful because then it gets you an idea to visualize any relationship between them. Let's go back to our data set. So what's neat about our data, I'm just going to delete these 2 because I don't really need them anymore. What's neat about our data is we not only have major salary information, but we also have how popular the salaries are. Do you think there is any relationship between how popular salaries are and how much money they make? I'm talking median salary. What? Salaries aren't talking about majors per 10,000. So obviously, accounting is more popular than architecture. Yeah, to be clear, I'm talking about the graduates and not necessarily people who have attempted. We don't have that data. We only have data on the people who graduated. So what do you think? Do you think there's going to be a relationship between these 2? Well, we can find out. The way you do that is if you go into Insert, you see there is this scatter plot option right here. Don't press it yet, because Excel likes it when you first select the data you want to use and then hit the button. The thing is, we want to select how many observations, we want to select how many variables? 2. So one way we can do this, but like when we highlight, right, we have to highlight stuff next to it. One way we can do this is we can just cut and paste, this and put it next to it and then do it that way. Another way to do it is to just highlight things we don't need. So I'm going to highlight this box right here. And then I'm going to hit the scatter plot. It's going to become blank. It's going to come up as blank. Does anyone know why? The scatter. Does anyone know why it's blank? Yeah, there's no second variable, right? We need observations that have both. Clearly, we don't have both because we don't have any other observations. But what I can do is if you mouse over and you see that crossbars I get, or the arrows right there, when I mouse over that line, I can now drag it to what I actually want. Right here. There we go. Make sure it's set up nicely. Now we have it. You want to include the row 1 or row 2, whatever this is, because it's going to assume the top row is a title. You see that I have that like weird red box at the top? That's just an artifact of that. You can move that thing at ground if you want to call it something else. But this is the setup. Whatever column is on the right will become your y-axis. Whatever column is on the left will become your x-axis. So if you don't want to default to that way, you just have to rearrange the columns. Does everyone get this? I'm waiting for people to read. So, yeah. Oh, so if you're getting percents, it's because you highlighted 50%. Let's just write it down. So if you get that 50%, if you get percents on your y-axis, it's because that you included 50% in your data. So select the value and then drag down that blue box so that 50% is not included in the data. So is there a relationship between these two variables? Between how popular a major is and how much it makes? Just give me your best guess. Does it? You don't think so? Yeah, I don't think so either. Right? It doesn't look like there's any relationship between these two variables. Now, granted, it's a little hard to see, especially right here on the far left, when a lot of variables are really next to each other. It would be nice if we could separate these out a little bit so we can maybe better see a relationship. And we can. But one thing to remember about scatter plots is that there are two different kinds of scales that describes the distance between each tick mark. These are what's called a linear scale. Does anyone know what a linear scale is? A linear scale, oh yeah. Yep, the same increment is added on, absolutely. Right. A linear scale means the same increment is added on. So on our x-axis, you see it's 100. So it goes 100, 200, 300, 400, 500. 100 is the increment. 100 plus 100 is 200. 200 plus 100 is 300. 300 plus 100 is 400, et cetera, et cetera, et cetera. The problem with this is that if there's something with like a lot of them have really low values, and so they're kind of all bunched together, it's really hard to kind of see what's going on. When you see business management with its crazy high value, it's like sort of way out here. This business management. One way we can fix this is by converting it to a different scale, where rather than a fixed value being added, a fixed value is multiplied. So we know what that's called. No, that's it. Yep. A logarithmic scale, or log scale, same increment is multiplied by. So we'll have a uniform increment of, say, 10, and then we'll have 1, 10, 100, 1,000. And this is really easy to do in Excel. Right-click the axis you want to change. You don't even have to select it first. You just right-click it. And you'll see there is a Format Access button right there at the bottom. Press that Format Access button. So right-click the axis you want to change and press Format Access. And then you'll see in this menu option there is the Logarithmic Scale option. Just hit Logarithmic Scale. Boom, you've changed it. 1, 10, 100, 1,000. These are the same, if you would take out a measuring ruler, these are the same distance, but this is the difference of, multiply by 10, multiply by 10, multiply by 10. And now you really see, is there any connection here? No, it really doesn't. Interestingly enough, There's no connection between how much a major pays and how many people take it. Now, if you pull on your economics hat, you can make a couple of arguments when you could say, well, maybe people care about lots of other things besides being paid a lot. So that could be the case. Another possibility is if something gets paid a lot, people are more likely to major in it. If people are more likely to major in it, then that kind of like brings down the salaries due to competition. So maybe that's what's going on. That seems a little strange because then there's no equilibrium, then people won't major in it anymore, so it'll go back down, and and then the salaries go down. So it's not really clear why there doesn't seem to be any correlation at all. It's a bit surprising. It might have to do with how the data is gathered. So what is the popularity values based off of? Like, what is that majors per 10,000? The number of graduates per major, right, who majored in that subject age 29 to 59. Annual salaries of college educated with that major, BA only. So one of the things that might be thrown off is that this does not include bachelor's degree only. So this, this includes people who went on to get advanced degrees. This does not. That might throw things off. But it's still kind of a surprising find. It also could be, too, that, if major is paid a lot like engineering, the reason why it gets paid a lot is because not a lot of people major in it. And so people are attracted by the salary, but they are dissuaded by the difficulty. Any questions? No. Great. One last thing. We've talked about time series before. Time is, of course, the element. You can create a time series graph simply by choosing the line button. Let me get rid of this thing. Oops, I think I deleted some observations. That's fine. The problem is, does this make sense as a time series? Here's the line button right here, insert line or area chart. Boom. Does that make sense? Anyone? No? So the question is, so I wanted to sort of get an idea of how to visualize this data. I'm like, I know what I'll do. I will see how it performs over time by highlighting everything and then making a line chart. Does that make sense? No. Why not? Yeah? Mm-hmm. And we can draw a logical connection between the first observation, the second observation, and the third observation of a time series. It makes sense that the first one is first, the second one is second, the third one is third, because the first one happened first, the second one happened second, the third one happened third. So it makes sense to make a line chart or a line graph, because line graphs literally connect things in some order. But here there is no order. It's alphabetical order is what it is. There's no connection between this one and this one other than they both begin with A. There's no connection between the first observation and the second observation because they both begin with A. That's stupid. Right? Why would we draw a line chart? Don't do that. Line charts are best for time series. Let's pull our time series now. So this data is from the Federal Reserve Economic Database, or FRED. I know, they're really cute, aren't they? It's out of the St. Louis Federal Reserve. They keep track of a lot of data. It's really great. Fred is a really great database. And this is the civilian labor force participation rate for women. Note this is a time series, starting in 1950s, I think in 1940 something, and going all the way up to present day.
What do we see about this time series? What do you notice? Yeah, it's increasing. Now it's decreasing a little bit. We're not really sure why. We might think it's childcare. Cost of childcare is really high. But we can see a logical story this time series.
Here is the labor force for men. What do you think the labor force for men looks like?
Oh, definitely not that low.
Well, let's see what it looks like. So how do you compare the civilian labor force for women with the civilian labor force for men? They seem to have an inverse relationship. That kind of makes sense, right? As women are entering the labor force, men are now competing with them, and some men just quite frankly can cut it. All right, and they don't get hired. Right. Which one do you think is higher now? Labor force for men or labor force for women? Women? Let's see what happened here.
So
You were looking at this, and you see it's decreasing. You're looking at this, you see it's increasing. And what are you looking at? What are you skipping over? You're looking at, yeah, you're missing the scale. Here are them combined. The top one is men, the bottom one is women. What? Oh, so this is percent. So it goes up from 90, 80, 70, 60, 50, 40, 30. So women right now, their labor force participation rate is 57.5%. For men, it's 69.3%. Right? You have to be careful when you're looking at data because you have to watch for something called truncation.
I want to make sure I get this done.
Something that's very common, especially in time series, but really in any chart, is truncating the axis. Truncating axis, which simply just means cutting off. We're changing minimum values. Note that this starts at 30. If you pull it up, it doesn't start at 0, it starts at 30. Similarly, for labor force participation for men, for women, for example, the lowest value it looks like it's 30 right here. For men, the lowest value is 67.5. Now, the good thing about truncation is you get to see what's going on. It's a lot easier to see the individual movements here because we have, it's a pretty narrow range. It looks like it's only 20 percentage points. So if you made it from 0 to 100, it would look pretty flat, as it did here when we expanded it, right? It looks a lot flatter now, and so it's hard to see those differences. The problem with truncating axes is it can lead to a lot of deception. It can lead to people seeing really big changes, but in the grand scheme of things, they're pretty small. People, for example, would note, like lately, the stock market sometimes like loses 100 points or loses 20. People are freaking out. But then you see what's been happening in the past like 2 years, and it's just like a very small dip in the grand scheme of things. But people see that truncated axis of that pretty narrow range, and they see this huge drop. Right, and you can see that here. Oh, God, it looks crazy. It looks crazy because this is the range we're working with. All right, 6 months, not so bad. 5 years, right? It's like a little speed bump. Max, what was going on? So just be aware of it. But that said, it is useful to be able to do because you can see what's going on. I think I have something in my notes right here actually about this. Here we go. This stuff. Here we go. Here's the Dow Jones Industrial Average for the year 2018. It looks basically flat. You see that I have, I mean, you can't see it, but like you pull up my lecture notes, you can see this starts at 0. It's hard to tell. But now let's change the bounds. Let's change it to a minimum of 20,000. Now we can see these individual movements move very easily. Excel will by default truncate your y-axis. Though truncation comes with dangers as mentioned, the above diagram is more readable, but it also looks more valuable than it is. Any questions? Last, if you ever want to print anything, this is a terrible thing. I just talked about how terrible this is. Let's not print it. Here we go. If you want to print anything, you select the picture and you hit Control P, and then you see it will just print that. If you don't select the picture and you hit Control P, then it's going to print the actual data. So you can print anything just by selecting a Control P. And of course, we didn't change anything in this because this is not something you would print. This is totally unreadable. You would add that, go to that plus sign. You can add the axes, you know, on either one, right, for the primary, the vertical. You can add the chart title and enter it. You can do lots of things to it. But what's interesting is actually working with and getting comfortable with the data. Any questions? No? All right, I'm going to let you go. Have a great weekend, everybody. I will see you next class.